Hey everybody, in this lab video I've challenged you to figure out with what force this spring inside of this cart, with what force that spring is going to accelerate this cart. So we're looking for the spring force. So what is that? When we press this little button here, you can see on the top of the cart, it shoots out that spring, and that's going to push against the wall of the track down here. Going to push against that and then send the cart zooming down the track. We'll record in slow motion with a bird's eye view so you can see distance information. As you can see on the track, we have a number line in centimeters that we can use to figure out the distance that our cart travels. We'll also have a stopwatch going in slow motion superimposed on the screen. You can use that to try and get some time values, and from that perhaps we'll be able to find stuff like the acceleration of our cart. The other thing you're going to need to know is the mass of this cart here, which we'll have to put on a triple beam balance for you to get, so I guess I'm going to have to go do that. But first, let's shoot the thing along and see what we get. Probably need to put a focus. Stop it. Okay, there's the spring loaded into the cart. Cart is right here. If you are able to see the numbers on the track, which you probably can't from this perspective, but in case we do end up using it, this is the starting position of the cart. The front of the cart is starting right there. 0 is way at the other end. So this is our starting position right there. Okay, I'm going to use a ruler to whack the top of the cart to set off the spring. Let's see, I could point out that right here, this might be useful. Let's put a final position. I showed you the starting position of the cart. What's the furthest point we can see? If we watch it until it gets to here, this right here, this line is the 100 centimeter mark. That's the 100 centimeter mark right over there. Okay, and we're starting over here on 23.3 centimeters. So if you watch in this distance, that would be some distance information that you should know. All right, let's whack the thing again. 3, 2, 1. Okay, so if you watch to go down to the 100 centimeter mark and you see how long that took, you could use that information to perhaps find, I don't know, acceleration. Our objective is to figure out what is the spring force that is the force accelerating the cart, and we are assume there's no friction because this is supposed to be nearly frictionless track. So you don't need to worry about friction. So we have a spring force that is focus. Stop. So we have a spring force that accelerates our car. This thing. You know what? Spring force that accelerates our car. We're assuming no friction. So when we use our second law equation, as we will have mentioned at the beginning of class, and which you should have encountered in our readings from last week, we say sigma F, or all of the forces acting on an object, is equal to mass times that acceleration of the object. So we can figure out our acceleration from the data we just collected about the time and the distance that our car traveled. We should be able to use a kinematic equation to figure out the acceleration. The mass, okay, we need to figure out the mass here because the spring force is going to be the main force there. It should be the only force horizontally accelerating our cart. So to figure that out, we're going to need to go find out what the mass of this thing is. So let's go get a triple beam balance. Okay. Whenever we use F equals ma, whenever we use F equals ma, we care about the mass of the thing being accelerated, the thing that has the forces acting on it, the thing that we drew as the dot in our free body diagrams earlier. So first I got to check and make sure this thing is actually zeroed. Remember how we do that with the triple beam balance? We should see our two lines line up right here, which I don't know if you can even really see that. So we have the screw over there to adjust it, to zero it. All right, now we're looking good. There's our focus. Look at that, beautiful. Okay. Now we're going to take our cart here, and why is that camera spinning to the left? Remember, with our triple beam balance, everybody should remember how to use these bad boys. We start off with our largest mass here, and we want to, of course, balance the thing. So these things should be about 500 grams or so. Oh, there we go. So here's our 500 gram indicator right there, or half a kilogram. We do this with kilograms because we're talking about newtons of force. You're going to want mass to be in kilograms. So 500 grams would be 0.5 kilograms. We're not quite balanced yet. We need a little more mass on there. It's hard to do this holding the camera. So there's a little too much. Back it up a little bit. Nice. Okay, so here's 500 grams, or 0.5 kilograms. 500 grams plus this front one is in grams, our front bar. So we've got 500 grams plus that many more. Now, how many is that? Just a touch, a tad more, not even half a gram above the 500 gram mark. But it's 500 grams plus however much you read off of that. And then you need to convert that number into kilograms, and that's what would go into our mass M for the mass of our cart. A, you need to calculate from the data that we've collected using a kinematic equation. And you want that A to be in meters per second squared. You want this M to be in kilograms, because kilograms times meters per second squared gives us newtons of force, and that's what we're looking at. What is the spring force that just accelerated that cart? So make sure this is in kilograms and make sure this is in meters per second squared. Okay. That's it.